So hello everyone, this is lecture 3 for the quantum mechanics. Today onwards we will start our first topic, that is black body radiation. Okay, so first we will study about the thermal radiation. So you have the idea about the thermal radiation because this word thermal is added with it. So what is the meaning of thermal? It is related to temperature, means any object which is heated will emit a radiation, and that radiation is called a thermal radiation. So every object exists in this world emit the thermal radiation because there is a temperature, that's why. So, and that emitted radiation will be continuous in nature. Means if you see the radiation means by any methods or the experiment, then you will find a proper spectrum of radiations from lambda to plus delta lambda. Okay, so that can lie in any region in the spectrum. Means we know about the electromagnetic spectrum that lies from the radio frequency to the gamma ray, radio frequency, microwave, then infrared, then visible region, ultraviolet, X-ray, gamma ray. So it can lie in any region. So in the normal room temperature we see that it lies in the infrared region, the radiations, because we can't see them by visible eyes, naked eyes, so that's why they lie in the infrared region. But at high temperature we can also see those, we can see them also. So let's see more things about the thermal radiation. Heated objects emit EM radiations of continuous wavelength from lambda to lambda plus delta lambda, and that are thermal radiations. It is called thermal radiation. At room temperature the body emits radiation in the infrared band only. Okay, so I already told you this. Now see, we know that we are getting radiations in the spectrum, but how do we get that spectrum? Is we know about this graph. This is a very famous graph or plot of the spectrum of radiations coming out of the heated object. So how do we get this graph? Means if this is the span, then you are seeing the span by the, is it the radiations emitted by the span or the reflected from the lights? So you see that you are seeing the span because of the radiation reflected, but not of the because of the radiations which are emitted from it. But to get the spectrum you need the radiations which are emitted by the object only, not reflected ones. So how to make an object something like that, which where you will have only the emitted radiations, not the reflected ones. Okay, so see, means you are seeing any object, this like you are seeing this object, so sun is hitting light on it, then the coming light you are observing, and same if you put something in the dark room even, then you see that there can be other radiations also which are you are observing. So there is no possibility by which you can measure the only coming out of the radiations means the radiations coming out from the object, inside the object. So how do we get this graph? Means if there are so much limitations that we can't find a body which can emit radiation, means from which we can study only the emitted radiations, so how can we make that body? So this is the body which is black body, by which we know what are black body. It is an ideal body that absorbs all radiations incident upon it regardless of the frequencies incident radiations. Now see, to get an object something like that which don't have the reflected radiations, we have to make an object which does not reflect any radiations. So we have to take an object which absorbs all radiation, only that objects can't reflect anything. So these are the black body which can't reflect any radiations, they absorb everything, and then the emitted radiations can be studied to get this graph. So it is an ideal body that absorbs all radiations incident upon it regardless of the frequencies of the incident radiations. So we have incident radiations, they will be absorbed, then there will be emission of the radiations. Okay, so but in this world we don't have the perfect ideal black body even. So how do we get this graph again? Let's see. First you need to understand about the thermal equilibrium. So what is thermal equilibrium? It's a thing when our system and surrounding are at the constant temperature. You know about it. So if some object is heating because of the incident radiations, then how to make it at the means equilibrium? So it must emit the radiation, only then it can be at the equilibrium. So that's why we say that, and the amount of energy absorbed will be equal to the amount of energy emitted, and in the form of radiation only. So if this is the black body and you say that 10 joule per second energy is absorbing in the form of radiations, then emission of the radiation will also have the 10 joule per second energy. Only then you will have the thermal equilibrium. You can take the example like a bike is standing in the sun rays, then it is going to blast if it doesn't emit any radiation. So after reaching a particular temperature, it will become constant for that, and that point is called thermal equilibrium. So at that point, the amount of radiations absorbed will be equal to the amount of radiation emitted. So that is the thermal equilibrium. The rate at which it absorbs the radiation, it emits the radiation at the same rate. So remember this. Now black body is what? It is a perfect absorber and perfect emitter. So if this is the black body, then it will emit all the spectrum of radiations, okay, in all the wavelength range. So now how to make a black body, because we can't have an ideal black body in this world. So how we can make the black body to get the curve, means how we get this graph again. So the experimentally what we do, we made an object something like this shape, and we have a small hole here. This is a very narrow end. So it is made something like that. Any radiation coming inside this, then there is this prism type and the mirror type structure which will reflect the radiations, and it will reflect it something like that, that it will be trapped inside it, means it will never go out. So any radiation coming inside will remain inside, and it will be absorbed and reflected inside it even only. So that's how we made a black body, means only emission after, when it will absorb these radiations, it will emit the radiation because of heating. So that radiation will coming out of this hole, and we will study that radiation. So that will be the ideal black body situation, where we will studying only those radiation which are coming out of the object only, not a reflected ones. Okay, so that's how we make the ideal black body. That's not ideal black body, but it's a 99% black body. So now how do we get that graph again? So the emission of radiations, let's say there is this emission of radiation coming out of the black body. So we have collimators here, they protect the any reflected radiations, and it will make it, means only we are getting this radiation outside. So we will place a mirror here to reflect this radiation. Now it will fall upon the prism, and we know what prism do. Prism disperse the radiation, means in the individual wavelengths by which this radiation is made, they will disperse inside this medium. We have seen in the prism, the sun rays got dispersed in the different colors, so we get the single wavelengths. Okay, now we have divided this radiation into different lambdas. Now they will fall upon again a mirror, and any lambda will be falling on it will go to this detector, means you can change this angle and you can take any lambda. Okay, that's how you can change the lambda, by just setting this, okay, orientation of this mirror. So let's say a particular lambda we get inside. Okay, let's see lambda 3 we are getting inside. Then this is a bolometer. What is bolometer? Bolometer is made up of a Wheatstone bridge, and this is used to measure the intensity of radiation or anything. How? This contains the Wheatstone bridge, something like this. And inside we have resistances, and these are thermistors, means their resistance change with the temperature. Okay, so when this radiation fall of particular wavelength, then we have this type of structure, and in the equilibrium condition we have no current in the galvanometer. But when the intensity fall upon it, the resistance will change and the equilibrium condition will disturb, and we will get some current in the galvanometer. So that current measurement will give us the intensity of that radiation. Okay, that's how we can measure the radiation's intensity. Now again, or changing the orientation of this, we will get something lambda 2 different, they're different lambda, and then again after changing we get different lambda, and we'll get different intensities here. Okay, so that's how we can measure for different lambda different intensities for this radiation. Okay, then we plot these all observations inside this graph, means for different lambdas we are plotting the different intensities. Then we will get this curve. At particular T1 we take this radiation and taken all the values, and we plotted this curve, we get it this curve. Then at a different temperature T2 we will plotted this curve, we get this curve. At T3 we get this, and T4 we get this. So see, that's how we get this graph. Okay, and here when you see that intensity will be in a increasing and decreasing order, means for a particular lambda there will be maximum intensity, and for the lower lambdas there will be minimum, and for the higher lambdas there will be minimum intensity. So this maximum intensity for a particular lambda with increasing temperature, this is shifting towards the this end, lower lambda. So as we see that temperature increasing, we see that maximum lambda for means that wavelength which are having the maximum intensity is going down. Okay, so what this says like means with increasing temperature you will have the curve inside this region, means lambda is decreasing, lambda will decrease this side and increase this side, and frequency increase this side and decrease this side. So lambda is decreasing means we are going in this region. So first it was lying in the infrared region. When the temperature is increasing, the maximum intensity is lying in this region and it is shifting towards this again and again. Okay, so that's how with higher temperature we'll go in this part. Okay, and with decreasing temperature we'll go to this side. So this is the graph which tell about this. Now we can, and this study was done in the 1899 by the Lummer and the Princeton. Okay, and this is called the BB spectrum, that is black body spectrum. So remember how we get this result and how we get this curve. Now there are many things we can take out from this. See, this is kind of line is forming. Okay, with the maximum lambda at particular temperature we have different maximum lambda. So for this temperature we have this one lambda, for this temperature we have this one lambda, this is shifting towards it. So we are seeing that lambda is decreasing with increasing temperature. So lambda is inversely proportional to temperature. So we can write lambda is inversely proportional to temperature, the maximum lambda. Now this lambda mt will be constant, and we have taken all the observations, and someone has carried out all the, this was the Wiens, his name was Wiens, who calculated all the values, and he find the value of this constant lambda mt, and that was 2.89 to 10 minus 3 meter Kelvin. So this was a very important result, and this is called the Wiens displacement law, and he got Nobel Prize for it. So this was a constant, and now see, this is a very helpful result. Means you have any object which is emitting radiation and you observe the spectrum for it, and you find it the maximum lambda m at which it is having the maximum intensity. Now you will just put the value of lambda m here and you will get the value of temperature. Means just seeing this spectrum you can find the temperature of that object. So that's how it is very helpful, and we can use this also to find the temperature of sun, because sun is a perfect black body. By taking its spectrum we can find the temperature of the sun also, and any distance object, means distance stars and all, so we can find the temperature of them also by having a big telescope and drawing the spectrum, just finding the lambda m value at which it is having the maximum intensity, so we can get the temperature. So remember this result. Now there is one more thing, that is Stephen's law. So the area under this spectrum is nothing but the total energy, total amount of energy. Now this energy emitted per second is power, and that power is proportional to temperature to the power 4. So by the observation Stephen find that it is proportional to T to the power 4, and this is Stephen's constant sigma, Stephen's Boltzmann constant we call it. So for ordinary body, the Stephen's law can be written as power T, means energy emitted per second by the black body, will be equal to sigma E T4, where E is emissivity and it is 1 for the black body. This will be 1, then you will get this formula for the ideal black body, and it is less than 1 for the ordinary black body, or the ordinary body, it can be any body. Means black body is not meaning that it should be black in color. Okay, it can be any body which is emitting the radiation. Okay, so these laws are applicable to it. So that's it for today. I hope you enjoyed this lecture. We will continue with the same energy in the next lecture. Thank you everyone.